Module 3, Lecture A, Broadcasting Rules. By the end of this lecture, you will be able to explain NumPy's broadcasting rules and determine whether two shapes are broadcast compatible. Apply broadcasting to perform element-wise operations between scalars, vectors, and higher dimensional arrays. And diagnose and fix common broadcasting errors by reshaping or expanding dimensions appropriately. Core broadcasting rules. Aligning array shapes. To understand broadcasting in NumPy, focus on how it lines up array shapes from the right, starting with the last dimension. If one array has fewer dimensions, NumPy pretends it has extra dimensions of size 1 on the left so the shapes can be compared. This right-aligned view lets NumPy decide which dimensions match directly and which can be stretched. Once you think about shapes this way, the broadcasting rules become much easier to see and predict. When NumPy combines a three-dimensional array, such as daily temperatures across cities, days, and times, with a one-dimensional array of daily adjustments, it lines up their shapes from the right. This means it matches the time dimension first and treats the smaller array as if it has extra leading dimensions of size 1. Each dimension is then compared in turn to decide whether the adjustment can be broadcast across all cities and times. By mentally aligning shapes from the right, you can quickly see when broadcasting will succeed or when the shapes are incompatible. Aligning array shapes from the right is more than a technical detail. It guides how you design arrays for efficient broadcasting. In financial modeling, placing the time axis last lets a one-dimensional time-based risk factor automatically broadcast across all instruments. In recommendation systems, putting the item dimension last allows a popularity vector to broadcast across all users. Thinking in this right-aligned way helps you predict how arrays will interact, avoid shape mismatches, and build data structures that work smoothly with broadcasting. Python code. Aligning array shapes. NumPy broadcasting works by aligning array shapes from the right, so the last dimensions are compared first. When shapes have different lengths, you can imagine adding leading dimensions of size 1 to the shorter shape so they line up conceptually. Two shapes are broadcast compatible when, for every aligned pair of dimensions, the sizes are either equal or one of them is 1. Using this rule, you can determine which pairs of shapes can be broadcast together in NumPy operations. We begin by importing the NumPy library, which is a key tool in Python for working with arrays and performing fast numerical calculations. Using NumPy allows us to handle array data efficiently and carry out complex operations with minimal code. This import sets up everything we need for the array manipulation and broadcasting examples that follow in the script. We create 3 arrays of 1s with different shapes to illustrate how NumPy broadcasting works. The first is a 2-dimensional array with 3 rows and 4 columns. The second is a 1-dimensional array with 4 elements. The third is a 3-dimensional array with size 2 by 3 by 4. These differently shaped arrays provide a simple setup for exploring how NumPy combines arrays of various dimensions. The function first finds the larger length of the 2 shapes so they can be aligned correctly. It then pads the left shape with leading 1s until it reaches this maximum length. The right shape is padded in the same way. By adding these leading 1s, the function makes it easy to compare the shapes and see how they line up from the right during broadcasting. The code first prints the original shape of the left array, and then its aligned version, where ones are added to the beginning of the shape so its length matches that of the right array. It does the same for the right array, showing its original shape and the version padded with leading ones. Finally, it uses the broadcast shapes function from NumPy to compute and print the resulting shape when these two arrays are broadcast together, illustrating how their aligned shapes determine the combined output shape under broadcasting rules. The code starts by announcing that the first example shows how a two-dimensional array aligns with a one-dimensional array. It then calls a helper function that takes the shapes of the two arrays as input. This function illustrates how the shapes line up from the right side, which is how NumPy conceptually aligns them. Through this, the example demonstrates how NumPy broadcasts operations between arrays of different dimensions. We look at how a three-dimensional array lines up with a two-dimensional array to understand NumPy broadcasting. A helper function is called with their shapes to show how NumPy conceptually aligns them from the right, inserting leading dimensions of size 1 when needed. This alignment reveals whether the two arrays are broadcast compatible and what the resulting shape will be. The example illustrates the general rule NumPy uses to broadcast arrays of different dimensions. In this example, we first announce that we are about to demonstrate incompatible shapes. We then try to align two arrays using a helper function. One is a two-dimensional array with 3 rows and 5 columns, and the other is a one-dimensional array with 4 elements. Because these shapes cannot be broadcast together, this operation raises a value error. We catch this error and print a message that includes the error details, making it clear that the shapes are not compatible for broadcasting. This script explains how NumPy decides whether two arrays can be broadcast together by aligning their shapes from the right. It shows that when a lower dimensional array is combined with a higher dimensional one, NumPy conceptually pads the smaller shape with leading ones, so the dimensions line up and can be broadcast. The first two examples use compatible two-dimensional and three-dimensional shapes to demonstrate successful broadcasting under this rule. The third example uses shapes that cannot be matched, leading to a broadcast error. Overall, the script highlights that for broadcasting to work, each aligned dimension must either be the same size or equal to 1. Expanding size 1 dimensions. In NumPy broadcasting, any dimension of size 1 can automatically expand to match a larger dimension when arrays are combined element by element. NumPy compares array shapes from right to left and treats dimensions as compatible if they are equal or if one of them is 1. When a dimension of size 1 is stretched, NumPy does not copy data in memory. It simply reuses the same value wherever needed. This allows, for example, a single column of values to be applied across many rows without storing duplicate data. NumPy broadcasting lets arrays with different shapes interact by automatically expanding smaller dimensions. For example, if you have daily temperatures for one city and a grid of temperatures for many cities over many days, NumPy compares their shapes from the right, matches the shared day dimension, and treats the single city dimension as if it were repeated across all cities. This means the one city's temperature pattern is applied to every city in the grid. The same idea applies when using a single discount rate across many products or a single risk factor across many financial instruments. Understanding how size 1 dimensions expand is key to predicting when broadcasting will work. A dimension of size 1 can stretch to match any positive size in the other array, as long as all the remaining dimensions are already compatible. If you have data with batches, samples, and features, it can combine with an adjustment array that has one batch and one sample, because those size 1 dimensions expand. However, if a feature dimension differs and is not 1 in either array, broadcasting fails and you get an error. By checking where the size 1 dimensions are, you can quickly see whether two shapes can be broadcast together. Python code, expanding size 1 dimensions. This segment will demonstrate how NumPy broadcasting works by expanding dimensions of size 1. We will focus on a simple example that combines daily temperature data for a single city with another array, showing clearly how the shapes change when broadcasting occurs. The goal is to highlight how a dimension of size 1 can stretch to match a larger dimension during operations. To keep the example easy to follow, the arrays will be small, and the printed output will be limited to fewer than 15 lines. We begin by importing the NumPy library, which is a core tool in Python for working with arrays and performing fast numerical calculations. NumPy provides the essential functions needed to create, modify, and combine arrays. It also supports broadcasting, which allows operations to be applied efficiently across arrays of different shapes. This import step sets up everything required for the array manipulations demonstrated in the code. We use a two-dimensional array in NumPy to store temperatures in Fahrenheit for several cities over several days. In this grid, each row represents a different city, and each column represents a specific day. The numbers in the array are the recorded temperatures, which makes it easy to organize, analyze, and manipulate the data for further work. We use NumPy to create a simple one-dimensional array that represents daily temperature variations for a single city, with the values 1, 2, and 3. This array serves as a basic example to show how temperature data for one city can be broadcast across data for multiple cities. By broadcasting this array, we can easily apply operations like addition across different dimensions of temperature data. The key idea is that a small array can be automatically expanded to match larger datasets, simplifying multi-city temperature calculations. We first check the shape of the city day grid, which stores temperatures for many cities over several days, to understand the dimensions involved. Then we check the shape of the array that holds daily temperatures for just one city. Knowing both shapes lets us verify that the single city data can be broadcast across the larger grid. Once we confirm the dimensions are compatible, we can safely add the one city temperatures to the multi-city grid in a single broadcasting operation. In this example, we add the temperatures from one city to a grid of temperatures for many cities and days. NumPy uses broadcasting to automatically stretch the smaller one-dimensional array so it lines up with each row of the larger two-dimensional array. As a result, the single city's temperature values are added to every row, applying the same daily adjustments to all cities. This produces a new array where each city's daily temperatures have been increased by the corresponding values from the one city array. To understand broadcasting, we first look at the shape of the resulting array to see how its dimensions have changed after the operation. Then, we examine the values in the result to observe the actual data produced by broadcasting. By doing this, we can confirm that the original one-dimensional array has been correctly expanded across the grid. This process clearly demonstrates how broadcasting works in practice. We reshape the one-dimensional array of temperatures for a single city into a two-dimensional array with 1 row and 3 columns. This reshaping adds a dimension of size 1, which makes the array compatible for broadcasting with the full grid of city temperatures. By explicitly aligning the dimensions in this way, we can clearly demonstrate how broadcasting works and ensure the operation behaves as intended. We first print the shape of the reshaped one-city temperatures array, which now has an extra dimension of size 1 to see how its structure has changed. Then we add this reshaped array to the city day grid and compare the result with the earlier broadcasting operation. Seeing that both results match confirms that explicitly adding a size 1 dimension produces the same broadcasting behavior. This verifies our understanding of how broadcasting works in this situation. This script illustrates how NumPy broadcasting works by using temperature data. It starts with a two-dimensional array for several cities over several days, and a one-dimensional array for one city's daily temperatures. When the single city data is added to the grid, NumPy automatically broadcasts it across all cities, so the result matches the grid's shape. The script then reshapes the single city data to add a size 1 dimension, and shows that adding this reshaped array to the grid produces the same result. This demonstrates that broadcasting lets NumPy expand size 1 dimensions automatically, making it easy to combine arrays of different shapes. Scalar and vector broadcasting. Scalar and vector broadcasting in NumPy lets you apply a single value or a simple list across a larger array automatically. When you combine a scalar with an array, NumPy conceptually stretches that scalar to match the array's shape and performs the operation on each element. For example, converting a grid of temperatures from Celsius to Fahrenheit can be done by multiplying by a constant and adding an offset without manually building matching arrays. In effect, the scalar is treated as compatible with any array shape and is expanded behind the scenes to fit all dimensions. Vector broadcasting extends the idea of applying a single value to an array by allowing a one-dimensional array, or vector, to interact with a matrix. For example, if you have a matrix of monthly sales and a vector of monthly tax rates, NumPy can align the vector with the matrix's columns when their lengths match. Operations like addition or multiplication then apply each tax rate to the corresponding column across all rows. Conceptually, the vector is repeated for every row, but NumPy does this without actually copying the data, using the same shape comparison rules as in other broadcasting cases. To check if a scalar or vector can broadcast with an array, compare their shapes starting from the last dimension and moving backward. And make sure each pair of dimensions is either equal or one of them is 1. Scalars are always compatible because they can expand to any shape. Vectors, which have a single dimension, must match the corresponding dimension of the array or be reshaped so they line up with the intended axis. For instance, a 7-element vector can align with a 7-day dimension in a larger data array. And if it does not align at first, reshaping or transposing the vector can make it broadcast correctly across the remaining dimensions. Python code, scalar and vector broadcasting. Illustrate scalar broadcasting by applying a single temperature conversion value across an entire grid, so one number is automatically expanded to match the grid's shape. Then, show vector broadcasting by applying a one-dimensional list of monthly tax rates across a two-dimensional matrix of product sales, where each month's rate is aligned with the corresponding column. Emphasize the shapes of the arrays before and after these operations, so learners can see how broadcasting rules work and build a visual intuition for how scalars and vectors expand to match larger data structures. We begin by using the NumPy library, a key tool in Python for numerical computing. NumPy supports efficient work with arrays and matrices and offers many mathematical functions for these data structures. In this script, it is used to perform operations on arrays, including broadcasting, which lets us apply arithmetic to arrays of different shapes in a fast and convenient way. We use a two-dimensional grid created with a numerical computing library to represent temperatures in Celsius across a small city. Each row in this grid corresponds to a different north-south position, and each column corresponds to a different east-west position. The temperature values are kept small so that the printed grid is easy to read and suitable for beginners. To convert a grid of temperatures from Celsius to Fahrenheit, we apply the standard conversion to every value in the grid. Each Celsius value is first multiplied by 1.8 to match the Fahrenheit scale. Then 32 is added to shift the baseline. NumPy uses scalar broadcasting to automatically apply these operations to every element, treating the single numbers 1.8 and 32 as if they were expanded across the entire grid. This allows the conversion to be done efficiently and element by element without writing explicit loops. We first check the shape of the Celsius grid to understand its dimensions and how the data is arranged in rows and columns. Then we check the shape of the Fahrenheit grid, which should be the same, to confirm that the scalar broadcasting worked correctly across the entire grid. Finally, we inspect the values in the Fahrenheit grid to see the result of converting each Celsius value to Fahrenheit, showing the effect of the scalar multiplication and addition on every element. We create a small two-dimensional array using NumPy to represent a sales matrix. In this matrix, each row stands for a different product, and each column stands for a different month. The numbers in the matrix show how many units of each product were sold in each month. The dimensions are kept small, so the results stay clear and easy to interpret. We define a vector of monthly tax multipliers for 3 months, and its length is chosen to match the number of columns in the sales matrix. Because of this matching size, NumPy can automatically broadcast the vector across all rows of products. As a result, the tax multipliers are applied to each month's sales data for every product without needing extra loops or manual repetition. We use vector broadcasting to calculate taxed sales for each product across different months. The sales units matrix holds the number of units sold per product per month, and the monthly tax multiplier is a vector of tax rates for each month. When we multiply the matrix by this vector, NumPy automatically broadcasts the vector across the matrix, aligning it with the last dimension. This applies the correct monthly tax rate to each product sales, producing a new matrix of taxed sales with the same shape as the original sales matrix. We first check the shape of the sales units matrix to see how many products and months it includes. Then we look at the shape of the tax multiplier vector to confirm that its length matches the number of months. Finally, we examine the taxed sales matrix, which is created by broadcasting the tax multipliers across each row of the sales units matrix so that the appropriate tax rate is applied to every product's monthly sales. This script shows how NumPy uses broadcasting with both scalars and vectors. It first converts a two-dimensional grid of temperatures from Celsius to Fahrenheit by automatically spreading the conversion constants across the entire grid, producing a new grid with the same shape. It then demonstrates vector broadcasting on a sales matrix, where a vector of monthly tax multipliers is broadcast across the rows to compute taxed sales for each product and month. By printing the shapes of the original data and the results, the script confirms that broadcasting correctly aligns dimensions and efficiently applies operations across the whole arrays. Broadcasting in practice. Row and column offsets. Broadcasting is a way to apply row and column offsets to a grid of values without manually reshaping data. For example, if you have a matrix of sales where each row is a product and each column is a day, you might want to adjust each product's sales by a fixed amount across all days. Broadcasting lets you use a one-dimensional array of these per-product adjustments and automatically repeats each value across all days in its row. The result is a new matrix where each row is correctly adjusted by its specific amount in a simple and efficient way. Broadcasting lets you apply a one-dimensional array of daily adjustment factors, such as promotions or tax rates, to a matrix of sales data where each column is a day of the week. The factors are automatically aligned so that each one is applied to its corresponding column across all products. Conceptually, the smaller array is stretched down the rows to match the matrix shape. This makes it possible to adjust the entire dataset efficiently without writing loops or duplicating data. Broadcasting is especially powerful when you need to apply both row and column adjustments to a matrix, such as correcting student test scores for individual performance and exam difficulty. You can treat rows as students and columns as exams, then use row offsets for personal improvements and column offsets for exam difficulty. Broadcasting lets you apply these adjustments in either order to produce a fully corrected matrix without manually changing each value. This approach is widely useful in areas like image processing and finance, where large datasets need efficient, systematic adjustments. Python code, row and column offsets. Use a small sales matrix to demonstrate how broadcasting works with row and column offsets. First, apply a set of row offsets so that each row value is adjusted in the same way across all columns. Then, apply a set of column offsets so that each column value is adjusted in the same way across all rows. This shows how broadcasting automatically expands these smaller offset arrays to match the shape of the sales matrix. We begin by using the NumPy library, a key tool in Python for fast numerical work with arrays. In this script, NumPy lets us create and manipulate matrices efficiently. It also allows us to apply row and column offsets using broadcasting, which means we can perform element-wise operations on arrays even when they have different shapes. We begin by creating a sales matrix using a numerical array, where each row represents a different product and each column represents a different day. The entries in this matrix are specific dollar amounts, such as $100, $120, and $130 for the first product over 3 days, and $80, $90, and $95 for the second product. Organizing the data this way makes it easy to perform operations on entire products or days at once, such as applying offsets to adjust sales figures later in the code. We use a row offsets array created with NumPy to apply fixed dollar adjustments to each product in our sales matrix. This array has two values, 5 and -3, which represent how much we want to increase or decrease the sales figures for each product. By applying these offsets to every row, we consistently modify the sales data for each product across all days. To adjust the sales matrix using row offsets, we add a set of offset values to the matrix so that each row is shifted by its own amount across all columns. We first reshape the row offsets into a column vector using the newaxis feature in NumPy. This reshaping lets each offset line up with its corresponding row. When we then add this column of offsets to the sales matrix, broadcasting automatically applies each row's offset to every element in that row. We create a column offset array with the values 10, -5, and 2, where each value corresponds to a specific day. These offsets represent how much we want to adjust the sales data for each day. By adding this array to the sales matrix, we use broadcasting so that each column in all rows is shifted by its matching day-specific amount. This prepares the data for consistent day-based adjustments across the entire dataset. We adjust the sales matrix by adding a set of column offsets to each row. The sales matrix holds the sales data, and the column offsets specify how much to adjust the values for each day. When we add these offsets, the same adjustment for a given day is applied across all rows. This uses broadcasting, which lets us add a one-dimensional array of offsets to a two-dimensional matrix efficiently, without writing explicit loops. The program first prints the original sales matrix, which shows the sales data in dollars. This initial display serves as a reference point for everything that follows. By presenting the unmodified data up front, it becomes easier to see how later adjustments and transformations change the sales values. Now we print the matrix after applying the row offsets to every column. This shows the result of adding each row's specific adjustment to its original sales values. By looking at this modified matrix, we can see how the sales figures for each product have changed based on the assigned row offsets. This step helps us verify that the row-based adjustments were applied correctly across the entire sales matrix. Next, we display the matrix that results from applying the column offsets to every row. This shows how each column adjustment changes all the values in the sales matrix. The printed output contains the original sales figures after they have been modified by the specific day adjustments. Viewing this adjusted matrix gives us a clear picture of how the column offsets affect the entire dataset. This script uses a sales matrix to show how broadcasting works in NumPy when applying row and column offsets. It starts with a matrix of product sales over several days. then adds a different fixed amount to each row to adjust each product's sales across all days. Next, it adds a different fixed amount to each column to adjust each day's sales across all products. The output displays the original matrix and the two adjusted versions, making it clear how row and column offsets are automatically expanded and applied through broadcasting. Featurewise normalization. Featurewise normalization uses broadcasting to normalize each feature of a dataset with its own mean and standard deviation in a single operation. Instead of processing each feature column separately, the means and standard deviations are stored in one-dimensional arrays. Broadcasting then automatically lines up these statistics with the corresponding feature dimension and extends them across all examples. This allows every row in the data matrix to be normalized efficiently and concisely at once. When normalizing a dataset of house features like size, number of bedrooms, and age, you can subtract the average of each feature from every row and then divide by the standard deviation of each feature. Broadcasting lets the system treat the arrays of averages and standard deviations as if they were repeated across all rows, automatically aligning each value with its column. This means you can perform feature-wise normalization efficiently without manually reshaping or copying the statistics, because the library handles the alignment and stretching of these values across the entire dataset. Broadcasting is especially helpful when working with high-dimensional data such as color images, audio spectrograms, or sensor readings. For example, if you compute a mean value for each color channel across a large image dataset, broadcasting automatically lines up these means with every image and every pixel in the correct channels. The same idea applies when normalizing audio frequencies or other features in complex datasets. Broadcasting takes care of the alignment and repetition for you, making feature-wise normalization efficient, seamless, and concise. Python code. Feature-wise normalization. We will demonstrate feature-wise normalization on simple house data using NumPy broadcasting. For each feature, such as size or number of rooms, we compute its mean and standard deviation. Then use these values to scale every row of the dataset efficiently. By paying attention to the shapes of the data and the feature statistics, we can see how broadcasting automatically stretches the per-feature means and standard deviations across all examples. This shows how normalization can be done compactly and efficiently without writing explicit loops. We begin by importing the NumPy library, a key tool in Python for numerical computing. NumPy supports large, multi-dimensional arrays and matrices and offers many mathematical functions to work with them efficiently. In this script, we rely on NumPy to perform array operations and to carry out feature-wise normalization on the dataset. We begin by creating a small dataset with a numerical array that represents 3 houses, each described by 3 features in imperial units. The columns store the size in square feet, the number of bedrooms, and the age of the house in years, while each row corresponds to 1 house. We set the data type to floating point values so that later numerical operations, such as normalization, are handled with sufficient precision. To begin normalizing the housing data, we first compute the mean of each feature across all houses. This means taking the average value down each column of the dataset, such as size, number of bedrooms, or age. The result is an array where each entry is the mean of one feature. These mean values serve as a baseline that we use to center each feature during normalization. We compute the standard deviation for each feature across all houses by applying a standard deviation operation to each column of the dataset. This gives one value per feature that describes how much that feature varies among the houses. Understanding this variability is important because these values are later used to normalize the data. We normalize each feature in the dataset by using broadcasting, which lets us apply the same operation across all rows at once. For every feature, we subtract its mean from each value, then divide by its standard deviation. This process scales each feature consistently and ensures the entire dataset is adjusted in a uniform way. We print the shapes of the dataset and the means to show how broadcasting works. The dataset shape tells us how many rows and columns we have, and the means shape tells us how many features there are. Even though the means form only a single row, they can be automatically extended across all rows of the dataset. This makes the shapes compatible for operations such as normalization. We first display the original dataset so we have a clear reference before making any changes. Seeing the raw data helps us understand its initial state and structure. Later, we can compare this original version to the transformed version to evaluate how featurewise normalization has affected the dataset. The code outputs a normalized version of the dataset, where each feature column has been adjusted so its values are centered around a mean of about 0. The normalized values are rounded to 2 decimal places to make the results easier to read. This normalization puts all features on a similar scale, which simplifies comparing them and supports clearer data analysis and visualization. This script shows how to perform featurewise normalization on a small dataset of house attributes using a numerical computing library. Each row represents a house, and each column represents a feature such as size, number of bedrooms, or age. The script computes the mean and standard deviation for each feature across all houses, then uses broadcasting to subtract the means and divide by the standard deviations. This process scales each feature so it has a mean of 0. The script prints the original and normalized datasets along with their shapes to illustrate how broadcasting is applied across the data. Batch scaling with broadcasting. Batch scaling is an important use of broadcasting in data science and machine learning because it lets you transform many examples at once without writing explicit loops. When you have a batch of high-dimensional data, such as images or audio, broadcasting allows element-wise operations between this large array and a smaller array of transformation parameters. The smaller array is conceptually repeated across the batch, so each example is scaled or shifted in the same way, without actually duplicating data in memory. This leads to shorter, clearer code and faster execution through optimized, vectorized operations in the numerical library. Broadcasting lets you apply the same operation across a whole batch of data without writing loops. For example, with a 3-dimensional array of color images, you can multiply by a single brightness value to scale every pixel, or by a 1-dimensional array to scale each color channel differently. The smaller value or array is automatically stretched across all images, positions, and channels during element-wise multiplication. This same idea also applies to other data, such as scaling financial time series or adjusting audio signals by channel gain. Batch scaling with broadcasting lets you apply complex transformations to many feature vectors at once by combining arrays of different shapes. You can store per-feature scaling factors in a one-dimensional array and a global offset as a scalar or another array, and broadcasting will automatically apply them across the whole batch. This makes it easy to chain operations like scaling and shifting in a way that matches your model's math. Using this method helps you design efficient data pipelines and models by avoiding explicit loops and improving performance. Python code, batch scaling with broadcasting. This section explains how to use NumPy broadcasting to scale batches of simple image-like data. First, it shows how to adjust the brightness of an entire batch at once by multiplying all images by a single scalar factor. Then, it demonstrates how to apply different scaling to each color channel across the whole batch by multiplying with a small vector that contains one value per channel. Together, these examples illustrate how broadcasting lets you efficiently apply both global and per-channel scaling without writing explicit loops. We begin by importing the numerical computing library that lets us work efficiently with arrays. Throughout the code, this library is used to create and manipulate arrays that represent image data. Using these arrays, we can apply operations such as scaling. Broadcasting techniques make it possible to perform these transformations quickly and compactly across entire images. We begin by creating a small batch of fake images using a four-dimensional array, where the dimensions represent the number of images, the image height, the image width, and the three color channels. In this example, the batch contains two images, each 2 pixels high and 2 pixels wide, with red, green, and blue channels. The array is filled with ones, so every pixel starts with the same brightness in all channels. We use a floating point data type so that later we can scale the pixel values precisely. We set a brightness factor of 1.5 to adjust all images in the batch. This single scalar value increases the brightness of every pixel by scaling its value by the same constant amount. The operation is applied uniformly across the entire dataset, so all pixels are brightened consistently. Broadcasting is used to apply this transformation efficiently without writing explicit loops over the pixels or images. In this operation, we brighten a whole batch of images by multiplying every pixel's brightness by the same scalar value. Using NumPy's broadcasting feature, this single value is automatically applied across all dimensions of the image array, so we do not need explicit loops. The outcome is a new array in which every pixel in every image has been uniformly scaled to be brighter by the chosen factor. We define scaling factors for the red, green, and blue color channels using a NumPy array with the values 0.5, 1, and 2. These factors control how much we dim or brighten each channel across an entire batch of images. The array is stored using a floating point type so that the intensity adjustments are calculated with good numerical precision. In this step, we apply per-channel scaling to images that have already been brightened. We multiply the brightened images by an array of scaling values, one for each color channel, red, green, and blue. broadcasting lets these three values be applied across all pixels and all images in the batch, without changing the batch or spatial dimensions. This independently adjusts the intensity of each color channel and gives us more flexible control over the final image appearance. We first check the shape of the original images array to understand the data dimensions before any changes. Then, we examine the shape of the brightened images array, which confirms that applying a brightness factor does not alter the dimensions and that broadcasting was applied correctly across the whole batch. Finally, we look at the shape of the scaled images array to verify that per-channel scaling also preserves the same dimensions. Together, these checks show that broadcasting maintains the batch and channel structure throughout all transformations. We first print the red, green, and blue values of the very first pixel in the original image to show its initial brightness levels. Then we apply the scaling operations and print the RGB values of that same pixel again. Comparing these before and after values reveals how the overall brightness and the individual color channels have changed. This makes it easy to see the direct effect of the scaling transformations on the pixel's color intensity. This script shows how to scale batches of image data using NumPy broadcasting. It first creates a batch of images where each pixel has the same red, green, and blue brightness. Then multiplies all pixels by a single brightness factor to make the entire batch brighter. Next, it applies different scaling factors to each color channel, cutting red in half, leaving green the same, and doubling blue while keeping the batch and channel dimensions unchanged. The script prints the shapes of the original, brightened, and scaled images, along with the RGB values of one pixel before and after scaling, to illustrate how these transformations affect the data. Fixing broadcasting shapes. Reading broadcasting errors. When you see a broadcasting error in NumPy, start by carefully reading the error message, because it usually tells you that the shapes of the arrays do not match. The key is to look at the numbers in those shapes and see which dimensions do not line up. For instance, adding a one-dimensional array of daily temperatures to a two-dimensional grid for multiple cities and days can fail if their shapes are incompatible. Treat the error message as a guide that points to the mismatch between your data structures and the operation you are trying to perform. When you see a broadcasting error, focus on the array shapes from right to left, because that is how broadcasting rules are applied. This helps you pinpoint which dimension is causing the problem. For example, if you adjust brightness in a batch of grayscale images with a one-dimensional array, and the error mentions the width, the mismatch is in that width dimension. If you work with financial data and the error mentions the leading dimension, the issue is in the outermost dimension. By checking each dimension in order, you can quickly find where the shapes are incompatible. When you see a broadcasting error, first decide whether it comes from missing dimensions or from incompatible sizes. Missing dimensions occur when one array has fewer axes, such as a matrix combined with a simple vector, and NumPy cannot automatically expand the smaller one. Incompatible sizes occur when both arrays have a dimension in the same position, but their lengths differ and neither is 1, so they cannot be repeated to match. For example, if sensor readings and calibration offsets do not line up, check whether you need to add a dimension or reshape the data so that the array structure matches the real-world quantities. Python code, reading broadcasting errors. Clearly show broadcasting error messages and focus on reading the shapes involved. Emphasize how to visually compare array shapes from right to left to see whether they are compatible. Use simple arrays to highlight when a dimension is missing or when sizes do not match, so learners can quickly recognize and understand broadcasting problems. We begin by using the NumPy library in Python, which is designed for fast and efficient numerical computations. NumPy is especially useful for working with arrays and performing mathematical operations on large sets of data. In this context, it will help us manage and manipulate temperature data organized across different dimensions. Using NumPy makes these tasks more efficient and easier to handle than with basic Python tools. We use a function from the NumPy library to create a two-dimensional array filled with zeros that represents a temperature grid. In this grid, each row stands for a different city, and each column stands for a different day. The array has 3 rows and 4 columns, meaning it tracks temperatures for 3 cities over 4 days. This structure makes it easy to organize and work with temperature data across multiple locations and times. We create a one-dimensional array using the zeros function from NumPy, setting its length to 5 to represent a short daily temperature series. However, this array is deliberately given a length that does not match the size needed for a later operation. This intentional mismatch in dimensions is used to illustrate how broadcasting errors can occur when array shapes are incompatible. We attempt an array operation that is likely to cause a broadcasting error by adding a two-dimensional temperature array to a one-dimensional array with an incompatible length. Because their shapes do not match, the operation fails and raises a value error. This error is caught in the exception block, where we handle it instead of letting the program crash. We then print a message that includes the error details so we can understand why the broadcasting failed. We create a one-dimensional array using the zeros function from NumPy and set its length to 4. This array represents a daily temperature series, with one value for each day in the two-dimensional temperature grid. By matching the length of this array to the number of days in the grid, we align their dimensions. This alignment ensures that any operations combining these arrays will broadcast correctly without shape compatibility errors. This line displays the shapes of 2 arrays, one representing a two-dimensional temperature grid for cities and days, and the other representing a one-dimensional series of daily temperatures. By printing these shapes, you can see the dimensions of each array. This confirms that the daily temperature series has been sized correctly to match the number of days in the grid. As a result, you can be confident that the arrays are compatible for operations such as addition, since their shapes align properly. We begin by creating a two-dimensional array using a zeros function from a numerical library with 2 rows and 3 columns to represent data for 2 assets over 3 days. This simple structure sets up a controlled example for studying broadcasting behavior. By later performing operations that intentionally mismatch the array's dimensions, we can observe how broadcasting works and what kinds of errors occur when shapes do not align properly. We create a one-dimensional NumPy array filled with zeros and give it a length of 2. This array is used as a benchmark, but its size is intentionally chosen so it does not match the leading dimension of another array. When we later try to combine these arrays, this mismatch causes a broadcasting error. This example highlights how incompatible array dimensions can lead to errors during array operations. In this example, We try to subtract a one-dimensional benchmark array from a two-dimensional asset day data array using NumPy. This relies on broadcasting, which lets NumPy operate on arrays of different shapes only when certain shape rules are satisfied. Because the shapes here are incompatible, NumPy raises a value error. The operation is placed in a try block, and when the error occurs, the except block catches it and prints an error2 message that explains the broadcasting problem. We create a one-dimensional NumPy array with 3 elements, so it lines up with the days dimension of another dataset. Matching the length of this array to the number of days ensures that operations like addition or subtraction work correctly. This alignment prevents broadcasting errors that occur when array dimensions do not match. This line prints a message that reports the shapes of 2 arrays so you can confirm they are compatible for broadcasting. The asset day data array has shape 2 by 3, and the benchmark good array has shape 1 by 3. Because their second dimensions match, operations can be applied across the days dimension without broadcasting errors. In short, this check verifies that the arrays are aligned correctly for element-wise operations. This script shows how broadcasting errors arise in NumPy when array shapes do not align. It first uses a temperature grid over several days and a daily temperature series with the wrong length, and the attempted addition fails because their shapes are incompatible. After correcting the daily series so its length matches the day's dimension, the addition works, demonstrating successful broadcasting. The script then repeats this idea with asset data and a benchmark that initially has an incompatible leading dimension, causing another error, and finally replaces it with a benchmark that matches the day's dimension so subtraction succeeds. Overall, the exercise highlights that to avoid broadcasting issues, array dimensions must be compatible when compared from right to left. Expanding dimensions with newaxis. In NumPy, you can use the newaxis feature to fix broadcasting issues by adding a dimension of length 1 to an array. This does not change the data, but it changes how NumPy interprets the array's shape so that dimensions line up correctly. It is especially useful when 2 arrays are almost compatible for broadcasting, but their shapes do not quite match. For example, you can align daily temperature data with city adjustment factors by adding a new axis, turning them into 2-dimensional arrays so broadcasting can correctly combine each city with each day. When working with customer purchase data, you might have one vector of product prices and another of discount multipliers for different customer tiers, but you cannot multiply them directly because their shapes do not align. Instead, you can imagine a grid where products form the rows and tiers form the columns. By adding a new axis to the prices, you turn them into a column structure, and by adding a new axis to the discount multipliers, you turn them into a row structure. This alignment lets NumPy broadcast the arrays together and efficiently produce a full matrix of discounted prices for every product and tier combination, without manually duplicating data or writing loops. When you use a new axis, the key idea is to picture where that extra dimension should go so your array shapes line up for broadcasting. Broadcasting errors usually mean that some dimensions do not match or one is missing. By knowing what each axis represents, such as time or location, you can decide where to insert a length 1 dimension. For instance, in image processing, adding a new axis to a color vector can make it match a grayscale image, so the color values spread correctly across all pixels. This makes the new axis a powerful way to fix shape mismatches and get predictable broadcasting behavior. Python code: expanding dimensions with newaxis. This lesson shows how to use the NumPy newaxis feature to expand array dimensions so broadcasting works correctly. You start with one-dimensional arrays that have incompatible shapes and see why they cannot be combined directly. Then you add new axes to reshape them so their dimensions align for broadcasting. Finally, you apply this idea to a practical example by creating arrays of product prices and customer discounts, and computing the full grid of discounted prices. We begin by importing the numerical computing library NumPy in Python. NumPy is essential for working efficiently with arrays and performing fast numerical operations. This capability is crucial for the tasks we will perform next, such as changing array dimensions and using broadcasting to apply operations across arrays. We begin by using the NumPy library to create an array that stores product prices. This array holds 3 numerical values, each representing the price in dollars of a different product. Using NumPy makes it easier and more efficient to work with these numbers and to perform further calculations on them later in the script. We set up discount multipliers for 3 customer tiers as fractions stored in a NumPy array. The values are 1.0, 0.9, and 0.8, which represent no discount, a 10% discount, and a 20% discount. Using these multipliers makes it easy to apply different discount levels to product prices later in the program. We begin by checking the shapes of the price and discount arrays and see that both are one-dimensional, each with only a single axis. This matters because in their current form, the arrays are not compatible for operations that rely on broadcasting. Broadcasting requires certain dimensions to match, and here they do not. By printing the shapes first, we make it clear that we must adjust these arrays before performing any element-wise calculations. We convert the prices array into a column vector by adding a new axis, which changes it from 1 dimension to 2 dimensions. This step is important because it lets the array behave like a column when used in calculations. With this new shape, broadcasting works correctly, so the prices can align with other arrays for element-wise operations. To make the discounts array work with broadcasting, we first convert it from a 1-dimensional array into a 2-dimensional row. We do this by adding a new axis at the start of the array. This turns the original discounts into a row vector. In this form, it lines up correctly with other arrays, so we can perform element-wise operations without shape mismatches. We check the shapes of the expanded arrays to confirm they are now compatible for broadcasting. The prices data has been reshaped into a column, and the discounts data into a row. With this setup, we can multiply them element by element across both dimensions. This prepares us to compute a full grid of discounted prices in the next step. We multiply the expanded price and discount arrays to form a grid where each row represents a product and each column represents a customer tier. This creates all combinations of products and tiers in a single structure. By relying on broadcasting, This operation automatically aligns the data without manual loops. As a result, we efficiently compute the discounted price for every product across all customer tiers in one step. The code prints a grid of discounted prices showing the final cost of each product after its discount is applied. In this grid, each row represents a different product, and each column represents a different customer tier. The print statement also includes a clear label so it is easy to understand what the grid of numbers means when you look at the output. This script shows how to use the newaxis feature in NumPy to make one-dimensional arrays work together through broadcasting. You start with product prices and customer discounts as separate one-dimensional arrays that cannot be multiplied directly. By adding a new axis to turn the prices into a column and the discounts into a row, you create two-dimensional arrays that are compatible. NumPy can then broadcast these arrays to produce a grid where each row corresponds to a product, each column corresponds to a customer tier, and each entry is the discounted price. This method efficiently computes all discounted prices at once. Reshaping for compatibility. Reshaping for compatibility means changing an array's shape so it aligns with another array under broadcasting rules, without altering the underlying data. When a broadcasting error occurs because dimensions do not match, you can often fix it by reshaping one array so its dimensions line up with the other. For example, a vector of daily temperature adjustments may need to be reshaped so it matches the day dimension of a temperature grid for multiple cities. This keeps the number of elements the same, but reorganizes them so broadcasting can be applied correctly. Reshaping is about adjusting an array so its dimensions line up with the operation you want to perform. For example, if you have three-dimensional sales data with regions, product categories, and months, and a one-dimensional list of monthly discounts, you may need to reshape the discounts so they match the month dimension and have size 1 for the other dimensions. This could mean turning 12 discount values into an array with one region, one category, and 12 months. Once reshaped in this way, the discount array can be broadcast across all regions and categories because the singleton dimensions can stretch while the month dimension aligns correctly. Reshaping arrays is important when combining data from different sources that are organized in different ways. For example, a medical researcher may need to align patient data with reference ranges by adjusting array dimensions so that patient and biomarker axes match, while other axes are set to size 1 for broadcasting. The same idea appears in image processing, where color channels, height, and width can be arranged differently depending on the library or dataset. By reshaping arrays to compatible forms, you avoid broadcasting errors caused by mismatched organization. Python code, reshaping for compatibility. This section shows how to reshape arrays so they are compatible for broadcasting when working with simple temperature data. You first see what happens when the shapes do not align, which leads to a broadcasting error. Then you fix the problem by reshaping one of the arrays so that their dimensions line up correctly. The focus is on using very small arrays and clear outputs so beginners can easily see how reshaping enables successful broadcasting. The script starts by importing the NumPy library, a key tool in Python for efficient numerical computing. NumPy is used to create and work with arrays, which makes mathematical operations faster and more convenient. In this code, it supports tasks like reshaping arrays and broadcasting, which help align data dimensions correctly for further processing. We use a two-dimensional array from a numerical computing library to represent temperature data. This array stores Fahrenheit temperatures for 2 cities measured over 3 days. Each row stands for one city, and each column stands for one day. Using simple integer values makes the structure easy to read and helps us clearly see how the data is organized. We create a one-dimensional array using NumPy to store temperature adjustments. This array has 3 values, each representing a daily correction in degrees Fahrenheit. Each value lines up with a specific day, matching the columns in our temperature dataset, so the corrections can be applied to the right days. In this example, the adjustments array is reshaped in an intentionally incorrect way to create a broadcasting mismatch. A one-dimensional array with 3 elements is turned into a two-dimensional array with 3 rows and 1 column, so each adjustment sits in its own row. This new shape no longer lines up with the city dimension of the temperature grid. As a result, the number of rows in the reshaped adjustments does not match the number of cities, clearly demonstrating incompatible dimensions for broadcasting. We start by printing the shape of the original temperature data, which is a two-dimensional array holding temperatures for 2 cities over 3 days, so we can clearly see its structure. Then we print the shape of the adjustments array, which was reshaped into 3 rows and 1 column. This reshaping does not match the city dimension of the temperature data. By comparing these shapes, we reveal the mismatch that would block broadcasting and show why reshaping the adjustments is necessary to make the arrays compatible. In this example, we recognize that trying to broadcast the 2 arrays would cause an error because their first dimensions do not match. The adjustments array has 3 entries in its first dimension, while the city temperatures array has only 2. This mismatch means the arrays cannot align correctly for broadcasting. We therefore indicate, with a message, that broadcasting would fail due to these incompatible dimensions. We reshape the adjustments array so it lines up correctly with the day axis, turning it into a structure with 1 row and 3 columns. This new shape matches the day dimension of the city temperatures array, which allows broadcasting to work properly. As a result, each adjustment value is applied to the correct day across all cities, enabling accurate element-wise operations. We reshape the adjustments array so it has 1 row and 3 columns, matching the day dimension of the temperature data and allowing broadcasting to work correctly. After adding these adjustments to the city-by-day temperatures, we check the shape of the result. It matches the original temperature data with 2 rows and 3 columns. This confirms that the reshaping was done properly and that the adjustments are applied correctly across all days for each city. We create the adjusted temperatures by adding the city and day temperature grid to the reshaped adjustment values. Broadcasting automatically lines up the dimensions so that each day's adjustment is applied to all cities. This produces a new array of temperatures after adjustment and shows that reshaping made the data compatible without changing the original values. This script shows how to reshape arrays so they are compatible for broadcasting using a small temperature example. It starts with a two-dimensional array of temperatures for 2 cities over 3 days and a one-dimensional vector of daily adjustments. When the adjustment vector is reshaped incorrectly, its first dimension does not match the temperature data. so broadcasting cannot align the values. After reshaping the adjustment vector to line up with the day axis, broadcasting works correctly. The final adjusted temperatures confirm that proper reshaping allows alignment without changing the original data values. In this lecture, you learn to explain NumPy's broadcasting rules and determine whether two shapes are broadcast compatible. Apply broadcasting to perform element-wise operations between scalars, vectors, and higher dimensional arrays. And diagnose and fix common broadcasting errors by reshaping or expanding dimensions appropriately. Congratulations on completing this course. Thank you for your attention. See you all in the next lecture.